This is the beginning of the Chapter 6 free response questions. We're going to start with number 11, and we're focusing on how random variables combine in this question. So here we see ACT scores for the 1.17 million members of the 2004 high school graduating class. That's probably like all seniors in 2004 who took the test, closely followed the normal distribution with the mean 20.9 and a standard deviation of 4.8. So if we look at all students who took the ACT in 2004, we want to choose 2 students independently and at random from this group. And the first part of the question asks us to identify what's the expected difference in their scores. And I think this was the part you guys struggled with the most, is identifying their difference, because it didn't seem natural to you to talk about what's an expected difference in scores. But if we define the difference as the difference between one score and another, I think it might be easier to kind of have this feel right to us. But it's really just the expected difference is the difference in the expected value of 2 scores. But since the expected value in any score is the same, the expected difference would be the expected value of the first score, which is 20.9, minus the expected value of the second score, which is also 20.9. And if we subtract those 2 values, we get 0. So it turns out that the expected difference when we subtract is 0. However, when we look for the standard deviation of the difference in the scores, this is where our old mantra, variances add, comes into play. So if we remember that variances add, the standard deviation of the difference is going to be found by starting with the variance of the difference. And the variance of the difference is the variance of the first score plus the variance of the second score, and then we're going to square root it to get the standard deviation. So doing that, we would take 4.8, we'd square it, we'd add 4.8 because that's the standard deviation of each expected value, we'd square it, and then we would take the square root. And when we do that, we get about 6.788. So that's the correct standard deviation for the difference in scores. So then, this was the really hard part. If I want to find the probability that the difference in the 2 scores was greater than 6, we're going to use a normal approximation here. It told me that the ACT scores followed a normal distribution, so it's appropriate to use a normal approximation in this problem. Okay, that was a terrible picture. Start over. But we know we can use that normal approximation because it told me that the scores followed a relatively normal distribution. And we're looking for the difference in scores. So we realized from part A that the difference in scores was expected to be 0, with a standard deviation of about 6.788. Now here we want to know, well, what's the probability that that difference is greater than 6? So that's a little bit less than 1 standard deviation above the mean. But this is the tricky part. If 6 minus 0, if that difference is greater than 6, the other thing that we have to consider is that the opposite can happen on the other end, right? If I have a score that's really low, then the higher score minus the lower score would give me a difference of 6. But if I had a score that was really high, the higher score minus the expected score of 0 would also give me a score difference greater than 6. So you actually have to consider both ends, or both tails, we would say, of these differences. So what we want to calculate is the probability that the difference in scores is greater than 6. That probability of the difference being greater than 6 is equal to 2 times the probability that my z-score is going to be greater than 6 minus 0 divided by my standard deviation of 6.788. So that works out to be about 2 times the probability that z is greater than 0.88. And using your calculator or a table, you get that to be about 0.3789. All right, so just to recap the rest of this problem, 6 minus 0, so this gives me my difference, and we want twice that because it could happen on either end of my picture. When I subtract and divide, I get 0.88, and then I multiply that probability by 2 to get the total expected probability of 0.3789.